Hi folks, this is lecture C3. So it's going to be asynchronous this time. We'll be back to synchronous instruction on Tuesday, or at least the availability of synchronous instruction for the next lecture. But otherwise, it's going to run just like a normal lecture. So there'll be an attendance exercises and you can fill them out. And so basically you'll have 24 hours after the lecture would normally run if we were doing it synchronously to fill in your attendance responses. And whenever questions pages come up, you can go to the questions, which I'm actually going to put in the Zoom chat. If you are viewing this on the Zoom link that I post, then you can actually view the chat alongside of it. So even though nobody's in the room with me here, still anything I put in the chat will be available there. And so you can find those things like the link to the questions page. So if any questions come up during the lecture, hit pause and send me a question, either through the questions link, through the discussions, through Slack, through an email, or just take down your questions as you're going. Again, feel free to pause me, put down your questions, and then afterwards, if your questions haven't been resolved by the end of the lecture, then send them away this way. So it's not synchronous, but we can make it as close as we can. So, all right, so let's move on then. So the only other announcements I have is that, there is that Canvas activity, which I think is due on Sunday. I'd have to double check to be sure, over chapter 3. You should also start reading chapters 4 and 5. 4 is pretty short, and I will put together a Canvas activity probably over the combination of the two of them that'll be available soon. But so that's that. There's a homework out there, and I think that is also due on Sunday. So make sure you're working on that. And even though I had to do asynchronous lectures today on Thursday, I should be available at my office hours at 4 p.m. in case you need me to see me there for homework help or whatever. So everything else, again, should be pretty normal. All right, so most of today will be going into a little bit more detailed justification of stuff that we talked about last time, and then extending it to understanding more about social welfare, not just across time, but just across people as well. So we're kind of closing out what happened in chapter 3 there with the kind of social welfare hooks there. So the first type of social welfare we're worried about then is this intertemporal social welfare, where we're thinking about an individual, but we're separating that individual into two individuals, an individual now in the present, and an individual in the later future. And benefits and costs to that individual, we can think about happening to two different individuals. And we need some equivalency to represent the benefits to the individual and costs to the individual in the future in the kind of interests or units of the benefits of the individual in the present. Now, if an individual in the present were to put money in the bank, then that money would accrue interest. And so $100 in the bank might be $105 next year due to interest. So that would correspond to a 5% interest rate. And so if I put $100, so if I convert this to pen here, if I were to put $100 in the bank in the present, and there was a 5% interest rate in the bank over a single year. So this T here is going to be equal to 1. So I'll just put maybe that in parentheses, T is equal to 1. Then that tells me that my future value is going to be equal to $105. So what that's saying is $100 that I invest now will be $105 in the future. Now, what that tells me is if someone says to you that they're willing to give you $100 now or $103 in the future, then you take the $100 now, because you can just put it in the bank and get the $105 in the future. If somebody tells you they'll give you $110 in the future, then you might consider taking that offer, because $110 in the future is better than the $100 now alternative put into the bank. So the bank's interest rate gives you a benchmark on which you can think about future costs and benefits. And that's why the interest rate at the bank we refer to as a discount rate, because it tells you how much you discount future rewards. So $105, we discount at a 5% rate. That means we divide it by 1.05, to find out how much it would be in the future, in the present. And so you either can think of the bank's interest rate as a benchmark rate, setting up your discount rate, or you can think more qualitatively, and you can say that I generally am going to value the welfare of people today more immediately, so I will get more benefit out of that than the welfare of people in 100 years. And so I care about the people in 100 years, but I don't care about them as much as the people now. Now, you can say, I care about them equally. Well, that just corresponds to a different discount rate, right? So if you care about them equally, then that means that your discount rate is like, you're not going to discount rewards in the future. You take them at face value. So that's a discount rate of 0. So we don't discount the future if we care about the future equally as the present. But most of the time, people care about the present more than the future, which implies a positive discount rate. And so now normally when we do these analyses in sustainability economics, we don't assume there's a single discount rate. We kind of do a sensitivity analysis to say, we know there's a variety of people who vary in their feelings about the future and the present. And so we are going to see how much our policy recommendation stands up if we have a discount rate of 5% versus a discount rate of 15%. And if we find that we still make the same recommendation for that whole range of discount rates, then we know that's probably a pretty good recommendation. We're not going to need to really defend it very strongly. But if we find out that our recommendation depends on you having a very high discount rate, then someone with a very low discount rate we know is probably going to disagree with us, and maybe we need to find a different argument or evaluate the basis of our argument or something along those lines. So that's the more kind of qualitative side of discount rates. On the more quantitative side, it's just easiest to use the interest rate of the bank as a benchmark rate on which we evaluate future rewards. All right, so with that, we can rearrange the equation. So we can divide both sides by this ugly thing, 1 plus r to the t. And then that gets the present value alone, like it is over here. And then so now we see that the present value, if you give me things in terms of future value, then I divide them by this 1 plus r to the t. And that discounts them so that those future rewards get divided down and get turned into present rewards. And just to make things cleaner, we are going to introduce this term, this beta, which we view as a marginal rate of substitution with the future. So this is basically equal to the how much do I get if I want to get a certain, well, it's more of if someone were to offer me an increment to my future utility called delta FV, that's my increment to my future utility, how much would I be willing to give up of my present utility? So if I have a beta value of equal to say 0.5, then that means that someone has to give me 2 units of future utility in order for me to give up 1 unit of present utility and still feel the same about it. Okay, so putting that a little bit more mathematically, we can say that there is a so-called intertemporal social welfare function, SW. And if I were to put in, let's say I had a present value, so I had a certain number of money in my wallet, and let's say it's, let's say I have $2 in my wallet. And then let's say then I've got a future value where I know that later on, like in a year, I am going to get $6. And I have a discount, or I have a marginal rate of substitution with the future of 0.5. That means I discount my future rewards by 100%. So I divide them by 2. So that gives me a marginal rate of substitution with the future of 0.5. So what that tells me is if I were to fill in this intertemporal social welfare function, then this present value, I have $2 currently, and then this marginal rate of substitution with the future tells me how much money I effectively have in today's dollars, considering what I'll have for tomorrow. So tomorrow I'll have 6, but when I rescale that by the half, then down in today's dollars, that's only 3. So my total intertemporal social welfare, considering both present value and future value, is equal to 5. So it's kind of like having a social welfare of 5, which is what I'm, if I were to sort of, this line here, I can think of this as my social welfare line. Or you can think of this as my present value line. And so I'm saying that I currently have 5 units of present value. Now, if someone were to say to me, okay, I'm going to give you an increment, a delta FV equal to 2, so that my new future value is equal to 8, then what this beta of 0.5 means says that, okay, in order to trade with you for that 2 that you'll give me in the future, I'm going to give you 1 today. So that means that my delta PV, so how much I'm subtracting from my present value, is going to be equal to 1. So in the future, I will, so not in the future, but after this exchange, then I will have $1 today plus my marginal rate of substitution in the future times how much I'll have in the future, which is 8. And that still adds up to 5. So my social welfare did not change because I exchanged according to my marginal rate of substitution with the future. And we depict that with indifference curves. So if I plot my present value on the y-axis, if I plot my future value on the x-axis, and then I've got my social welfare function of 5, then initially when I had 2 versus 6, so I had 2 units of present value. Well, let's say that's right here, 2 units of present value. And then 6, well, that's probably way out here, but I'm going to fudge it just to make it easier to plot. And let's say it's around here. So, or maybe just, I'd like to land on this line. So I'm going to maybe put it here. So let's pretend that this corresponds to 2 units of present value and corresponds to 6 units of future value. Now, if I'm going to change my pen color here to, I don't know, blue. And so now what we're saying is then, okay, well, if you give me 2 more units of future value so that I'm up to 8, then if I want to stay on this same indifference curve, then that means that I'm going to decrease my present value by 1. So this here, so I'm on the same indifference curve here. These 2 outcomes, me having $2 today and $6 tomorrow, and me having $1 today and $8 tomorrow, give me the same present value, the same, converted into today's utility, it's identical. I have the same utility. It's the same intertemporal social welfare. That's why they fall on the same indifference curves. All right. So I want to pause there and see if anyone has any questions. If you do, again, you can submit them on Slack in the discussion board. You can go to the 325 questions link that I put in the chat, which you can view on the in the ASU Zoom link, the cloud link for this lecture. So we'll pause here, collect your thoughts, see if you have any questions, to see if that makes sense. All right. So you're back from pause, and so hopefully that makes sense. So moving forward, we know that we've seen indifference curves before, and usually when we see this framework, we combine indifference curves with a budget constraint line. And that's how that budget constraint line tells us what the right balance of these 2 goods is going to be to maximize our utility. And so the question is, there's something like a budget constraint line when we think about multiple periods over time where we're consuming a limited resource. In this case, the limited resource would be the budget, would be the amount of money in our back pocket. If I have $100 in my back pocket and I go to the grocery store today and I spend 25, then it leaves me 75 bucks to go back to the grocery store later in a different time period. So of course, I'm going to get most of my value from my present reward. So I'd like to spend all $100 in the grocery store now and just maximize my value. But it turns out that if I do that, I'm going to starve next week. So if I need to stretch this $100 over both weeks, then I need to find the right balance of how much to spend today and how much to spend tomorrow, where my limited resource is the money in my pocket, to the money in my wallet. So if we think about that, we can generalize this message to a broader picture of scarcity, and to think about oil in the ground, for example. How much do I harvest now versus later? Water, etc. So that's kind of the model that we started with last time. And last time we said in a non-renewable resource model, a 2-period non-renewable resource model, this capital T is kind of like the money in our wallet. And Q here is kind of like the amount that we spend this week at the grocery store. And T minus Q is kind of like the amount of money left over we spend at the grocery store next week. So if we get paid every 2 weeks, then we know that whatever we don't spend this week, we can just spend all of it next week. And then we'll get paid at the end of next week and start the process all over again. So that's kind of what we're picturing here. But instead of picturing it dollars in our wallet, we can picture it as some other resource that, for whatever reason, we're only focusing on 2 periods right now. And it turns out these 2-period problems work well, because there's a way to take the results from your 2-period results, and then after you're done in the first period, you can shift and then think about the second period as kind of a new first period, and then keep shifting over and over again. And we'll get to problems like that later in the class. For now, we're just motivating this idea so that we can kind of get this graphical framework to think about this. All right, so for every choice I make in the current week, it changes what's available the next week. All right, that's what we covered last time. And now if we want to go more in detail of that, then let's try to bring in the graphs from before then. And so over here, I've got my present value, benefits and costs. So this is my present value, and here's the nice concave benefit function, and here's the nice convex cost function. And this here is my future value, and it is the benefits in the future and the costs in the future. Now, if I'm only focusing on the 1-period problem, I'm not focusing on how these 2 periods are combined. This is like if I got paid every week. So you get a new paycheck every week, you can spend the whole paycheck on groceries 1 week, and then you get a new paycheck, and then you can do the whole thing again the next week. If I'm only focusing on the 1-period problem, I don't have to divide it across 2 periods, then I can just say marginal benefits are equal to marginal costs in the current period. And that would be equivalent to maximizing the distance between these 2 curves, the benefit curve and the cost curve. And so we know that if I were to spend my entire budget, or to use up all of the oil or something like that, although my benefits, my raw benefits are maximized, the amount of effort I had to use in order to get all of that oil out of the ground is also maximized. And so the difference between the benefits I reaped and the effort I put into to get those benefits has been actually reduced. So there is an intermediate level here, which I might call QP star. So this is the present value star, the maximal value that maximizes the economic efficiency, that maximizes the difference between benefits and costs. And that's what I do if I was only focusing on the present. Similarly, if I was only focusing on the future, there is the same QF star, which is this intermediate level of consumption in the future, which maximizes the difference between the future benefits and the future costs. All right. Now, scarcity couples these 2 periods together. So ultimately, I don't have a paycheck every week. I have a paycheck every 2 weeks. So whatever I spend, or whatever amount of resource I take out of the current period, I have less resource that I can take out of the next period. So I shouldn't represent this as if it's an independent decision variable, QP and QF. Really, there's only one decision variable, Q, how much I spend in the current period. So let me reformulate. So now I just have Q in the present period, and I have T minus Q in the future period. So I still have the same benefit and cost curves. So here's my benefit to the present. This is my benefit in the future, my cost in the present, my cost in the future, and my net benefits in the present, my net benefits in the future. But look at what I did. is that now I've got my Q here, and instead of having a QF, I have a T minus Q, where this Q here is just Q, the present Q, QP. So this now makes it more realistic. It kind of shows that whatever decision I make in the present is going to fix the decision completely in the future. And that's what that formula does right there. All right. So now that I've done this little exchange in formula, then I can change the way I plot these graphs. So it's a little funny that I've got Q as an increasing axis here. But if you think about it, it's almost like as I increase my consumption in the present, what I'm actually doing is decreasing what's available in the future. So if I was over here in the present, setting Q equal to 0, that is necessarily going to set T minus Q. So that'll make T minus Q equal to T. And so if I'm experiencing 0 net benefit over here in the present, in the future, I'm experiencing this net benefit between this benefit and this cost because I am putting everything in the future. So as I sweep from left to right, as I sweep over here in this direction, what I'm doing is I'm starting on the right-hand side of this graph and sweeping in this direction. So what I'm going to do is I'm just going to try to make those directions the same. And so here's a little animation. Wait for it. I just took the net benefits curve and I flipped it around. So this curve here, so if I go back, this curve that I'm plotting is the widening space between the benefits and the cost. That's why it's hump shaped. And I'm going to take that net benefits curve from the present, and I'm just going to mirror it, and that will be the net benefits curve in the future. And then that allows me to use the same Q to represent both my present value net benefits and my future value net benefits. And so now this is really nice because as I sweep this decision variable up, then in order for me to figure out what my future value is, I just find the same spot. So if I'm here in my present value, that corresponds to this point here, then I go to the same point. So I take this same distance and I say, okay, that is here in my future value, which corresponds to this point over here. And that is a different point in this hump because this hump on the right is a mirrored version of this hump on the left. So all we've done is kind of mirrored those two so that we have a way of bringing those two things together. And that's nice because if I gave you a formula for this net benefit curve and this net benefit curve, you could, in principle, solve for this social welfare function. You could plug in the formula for the present net benefits. You could plug in the formula for the future net benefits using T minus Q in here. And then you could scale the future net benefits by the marginal rate of substitution with the future. And then if you simplify all those terms algebraically, then that gives you your social welfare function in whatever shapes come out of that. All right, so another little animation. I would like to now put those two hump-shaped net benefits curves together on this axis here, where we have the present value on the vertical axis and the future value on the horizontal axis. And all I've done is I've taken that curve that was the mirrored curve that had on the right, and I just lined up its future value, its vertical axis, to the future value axis on this curve up here that is the curve we use to show our social welfare and difference curves. And so that's all that we see here. So these two axes are linked up. They're just tied together so that they're moving in the same direction. And then likewise, the present value axes, those two are locked together. So this curve here is kind of like a backwards version of the present value curve from the previous slide, where now as I increase Q, I'm actually moving in this direction. And as I increase Q, I'm moving in this direction. So this shows me why I get this teardrop shape here, as we'll step through the steps here in a second, is that like right now, I'm at a point where Q is equal to 0. So Q is equal to 0. Well, Q is equal to 0, so in present value, when Q is equal to 0, then I have a present value of 0. But in future value, when Q is equal to 0, Q in the present is equal to 0, that means I get to use everything in the future. So my future value is non-zero. So when I put both of those two together on this future value, present value axes, then I get this point here where I've got 0 present value and a non-zero future value. And as I increase Q, I'm basically moving diagonally, because I increase Q, which is my consumption in the present. I'm going to be moving up this curve, and at least initially up this curve. So as I increase my present consumption, I am going to be increasing in my present benefits initially. And in the future, I'm actually going to also be increasing in my benefits in the future, because the one period solution is actually not to use everything. And that's why initially forcing myself to use less in the future is actually better. So this is a Pareto movement, actually, to go from consuming everything in the future to consuming some in the present and some in the future. I actually end up improving both utilities, the present value and the future value. That's a Pareto improvement. All right, so now I've increased Q a bit. So I've increased Q near the point where I maximize my future rewards. And so by increasing Q to that point here, that also has increased Q to this point here. And if I would have scaled these things properly, then this length distance would be equal to this length distance. So I'm sorry that I didn't get the scaling quite right. But as I'm moving along there, then I get a certain present value, which corresponds to this point here. And I get a certain future value, which corresponds to this point here. And that's what gives me the coordinates of this thing. So as I move from Q equals 0, which is down here, to this intermediate level, which sort of maximizes my future value, I'm rotating up along this line here. If I keep increasing Q, I keep consuming more in the present, then I can move up along this curve and end up maximizing my present value. And by moving up along this curve, so by moving this direction, I'm also forcing myself to move in this direction. And it turns out that although I now have maximized my present value, I've gone over the hump, and now I'm starting to decrease my future value. So for the maximal present value level, which corresponds to this on the kind of y-axis, then now I'm at a lower value than I used to be for my future value. And so that I used to be over here, and as I increase Q, I further rotate down this direction. And so I can keep doing this, and you can hopefully see that it just sketches out this circle, that I have this dashed circle all around here. So then the question is, how do I maximize my social welfare, but my intertemporal social welfare? Where on this curve is the maximal balance of present value and future value? And in order to answer that, I need to know what my marginal rate of substitution is with the future. I need to know exactly what this beta is. So in other words, it depends on discounting. So I need to know my discount rate, or I need to know how much I'm willing to trade in present numbers and to get future numbers. So, so let's say I know that. Now, the next part, I'm going to show you a little bit of calculus. Now, for those of you who haven't had a lot of calculus, I don't want you to worry too much about it. I'm primarily showing you this to try to show those who have had a little bit of calculus where these funny rules, geometric rules, come from. So I just don't want you to take for granted that you know, there's points of tangency, and points of tangencies are always good. I want to show you why the points of tangencies are good, and I'm just showing you a little calculus to justify that. I am not going to ask you to do this calculus yourself. I'm not going to ask you to do these level of numbers. The math that we will do ourselves will be kind of post-calculus, like after the derivatives are taken and all that's left is algebra. That's the math that we will primarily do in this class. But for those of you who have seen the calculus, I want you to at least have some exposure to this so you at least see where it is. If you're in the middle of calculus right now, then kind of just try to keep this in the back of your mind. And when you get to this sort of stuff in your calculus classes, then hopefully then it'll give you some context to understanding how useful that calculus might be. All right, so remember that this is the thing that we want to maximize, our intertemporal social welfare function. And if you remember from calculus, how do you maximize functions? Well, you typically look for stationary points. You take the derivative of them, the derivative of those functions with respect to the thing that you're trying to maximize. So in this case, it's how much I currently am using in the current period, the one period, and you usually set them equal to 0, and that's a so-called stationary point. And there's other things you need to do to make sure they're not inflection points or minimums and all that, and I'm just gonna sweep that under the rug and just assume this is all we need to do. So if I set that derivative equal to 0, over here, that's what I've done here, is that I've got my my social welfare function. So sorry, this is meant to be an S, social welfare, my intertemporal social welfare function. And if I were to set that thing equal to 0, then because my derivative operation is linear, then what that actually is equal to is me taking the marginal net benefit, so taking the partial derivative of the net benefit, and then adding in the discounted version of the future marginal net benefit. So this is my present value net benefit. This is my future value net benefit discounted by beta. And that just came from pushing the beta through the derivatives and then breaking the derivatives up. Now this thing here, if I want to solve for the Q that makes this true, I can just move things around so that this doesn't, so they've got things on both sides of the equation. And that gives me this thing here. So this is telling me that my marginal benefit in the present is equal to the negative marginal rate of substitution of the marginal benefit of the future. And I can do a little bit more algebraic rearrangement. And so this now shows me effectively a comparison of my marginals. This is saying here that my marginal benefit in the present, so that you can think of this as a marginal benefit in the present, divided by my marginal benefit in the future is equal to negative the marginal rate of substitution with the future. So last time we talked about the marginal rate of transformation, and that's basically what we're getting here, is what the thing on the left-hand side here shows you that if you were to stay stuck to this circular curve here and wanted to move along that curve, then what this thing on the left is showing you is how much you would have to transform of present value into future value in order to stay on that curve. That's the marginal rate of transformation. Now we can simplify that by kind of dropping the DQs. So this is a kind of a simplified version of my marginal rate of transformation, which we introduced last time. And it gives me this kind of new looking partial derivative, which is how do my benefits in the present change as I change my benefits of the future. And geometrically, I can depict that as if I draw a tangent line relative to this curve here, this PPF, this frontier up here, then at this point of tangency, the slope of this tangent line is this marginal rate of transformation. So this represents how much I have to give up of one thing in order to keep moving along this line. So if I want to give up a little bit of the future and to gain a little bit of the present and stay along this efficient frontier, then this tells me exactly how much I have to do in the marginal units in order to keep moving along this train track. That's all this is showing here. And what this is telling me down here is that I am going to maximize my utility when I find the point of tangency whose slope is going to be consistent with my marginal rate of substitution. So my marginal rate of substitution is here. And basically, when the marginal rate of transportation has the same magnitude as the marginal rate of substitution, that will be my utility maximizing result. And that's what's being shown down here. To see that more graphically, we can say that now I've put these lines here. These are my, remember, these are my social welfare functions. There's my social welfare indifference curves. And so these indifference curves are sloped according to the negative marginal rate of substitution with the future. And so you can think of it again, this is the marginal rate of substitution with the future. And there is some point where the indifference curve pierces this frontier and is tangent to it there. And at that point, that is going to be the optimal balance between present value and future value. So putting it another way, if I spent everything in the present value, so Q is equal to T, then I have nothing left in the future. And so I get no benefit in the future, I get all my benefit in the present, but that doesn't even maximize my present value, so I know that's probably not going to be right. And what this point of tangency up here is saying is that the zero rewards that I'm getting in the future combined with the suboptimal rewards that I'm getting in the present are not kind of like where I want to be. They're not maximizing my utility. And so I need to move up along this curve to reach higher levels of social welfare. And this point of tangency is going to be the highest that I get to. And this one is going to balance things in terms of how I feel about the future value and the present value. So if I put everything into the future, then that also isn't going to be optimal. I'm going to be at an even lower social welfare, because putting everything in the future here is I get no benefit out of the present, and any benefit that I get out of the future is going to be discounted. And the benefit I'm getting out of the future isn't even maximized for the future. So it's just a really bad place to be. And so I'm at an even lower indifference curve in social welfare space. So we can see that really for this particular scenario, I should be back here. This maximizes the 2-period discounted benefit in the present and the future. This represents that I do care a little bit about my future rewards, and I care about my present rewards. I care about my present rewards more than my future rewards, but I do care about my future rewards enough that there's a mixture here between my present value rewards and my future value rewards, and that mixture occurs at this point here, where my marginal rate of transformation is equal to my marginal rate of substitution. And remember, the slope of this thing is the negative marginal rate of substitution. And the slope of the tangent line at any point along this frontier is the marginal rate of transformation. And then clearly at this point, MRT is equal to MRS. And that is the utility maximizing solution. And that is another version of the equimarginal principle. Now, if I change my discounting to where I do not care about the future, if I do not care about the future, then what I'm going to do is I would set my marginal rate of substitution in the future equal to 0. That would set my discount rate equal to infinity. So that is, up here. So you can imagine that I have a discount rate equal to infinity. And so it's like getting infinite interest at the bank. If you got infinite interest in the bank, then you would never accept any money from anyone else in the future, because any money you could get in today, you just put in the bank and it's infinitely magnified. So you do not care about future value. So that's why it's an infinite discount rate corresponds to a marginal rate of substitution of the future equal to 0. And that corresponds to having social welfare and difference curves that are horizontal. When your social welfare and difference curves are horizontal, you only care about present value. And so your optimizer is going to optimize the present value. It's going to bring you to the maximal amount of present value. Now it just so happens that the optimal amount of present value does not use the whole resource up. So some resource is left over for the future. And so you do get some future value out of it. It just turns out that because your beta is equal to 0 over here, that you don't care. You just throw it away. You may as well burn that. You know, you don't, it doesn't matter to you. So that gets killed because your beta is equal to 0. But it just so happens you do have some left over, because the optimal thing to do when you're maximizing the present value is not to spend it all. It's to spend an intermediate amount. And that's because costs increase convexly and benefits increase with concavity. On the flip side of things, if you had a beta equal to infinity, so this would be kind of like a, so this here is, so you can, if there's no, you know, I could say, imagine this is a beta equal to infinity. This is kind of like this weird case where the discount rate would be equal to -1. Then that means that you really, really strongly prefer future benefits, and you don't care at all about present benefits. And that gives you these vertical lines. And then not surprisingly, they come to a point of tangency with the PPF, where you maximize your future value. So that's exactly consistent with what we expected. Now, if you're somebody who cares equally about the future and the present, you're going to have a beta equal to 1. And when you have a beta equal to 1, that corresponds to a discount rate equal to 0. So you don't discount future rewards. You care equally about the future rewards, and that gives you a beta value equal to 1. And so the symmetry in this teardrop combines with the symmetry in these 45-degree angle. So this is like -45 degrees here, because it has a negative slope of 1. And that means that your point of tangency is going to be where you equally balance present rewards and future rewards, so that the right here, the present value is equal to the future value. So your intertemporal social welfare function basically has a beta here equal to 1, so that you're just equally adding PV and FV. And so the only way, since you equally balance them, you're going to spend half of the total today and half of the total next week. Now, in reality, that's usually the extreme. Usually, we don't ever care about discount, or we don't ever get to the point where we focus on future benefits more than present benefits. So that's kind of our limit. And there is no reason for us ever to go beyond a beta of equal to 0, because at, you know, so you, like a negative value here implies that gets into it just does, it's a little bit nonsensical for a negative value, because it's almost like the thing is good today, but it's bad tomorrow, or it's bad today, but it's good tomorrow. And so that kind of is this weird thing where you might want to get rid of a lot of it. You know, you don't want to use it, all of it, any of it today. That maximizes your utility. But then tomorrow, you want to, so it's just weird, you know. So for a normal situation here where you get benefit both today and tomorrow, then you're only going to be limited to where beta is either equal to 0, or beta is in between 0 or 1, or at the very maximum beta is equal to 1. And so we are only really going to be focused on this part of the frontier. And so conceptually, as you're changing your marginal rate of substitution, what you're doing is shifting from here on the right, where you care about future value just as much as present value, to here on the left, where you only care about present value. And then the optimal place to be in between is just going to depend on where your beta is. And so you're going to, as your beta increases towards 1, you rotate this way, and you effectively start decreasing some of your present value, and you increase some of your future value as you start putting more interest into the future. All right, so this is a good time for questions. We basically just covered all of the stuff that we covered last time. So if you have any questions that have accumulated, again, I will just put into the chat so you can see that. If you're watching this on the Zoom cloud recording, you can check out the chat or post something into Slack or the discussion groups, or send me an email or send a TA an email. Just take some time to gather your thoughts here. You can also put them in the muddiest points. Don't forget there's a muddiest point due Sunday. All right. Okay. And maybe let's do, because we haven't done one yet, let's just hop to an attendance question. All right, so I'm just gonna jump ahead to an attendance slide here. And so at this point, so I'll put the URL in the chat. So let's do an attendance exercise. And the question on the attendance exercise is, what does the T stand for in MRT? So I'll tell you it's marginal rate of what? What does the T stand for? That's our attendance exercise so far. I'll give you a moment to gather your thoughts there. And we don't have much more left in this lecture. So this lecture was primarily to get us thinking about where that funny teardrop shape comes from in our kind of intertemporal social welfare space. All right, so let's move on then. All right, so moving forward, we have so far been talking about intertemporal social welfare. So we're sort of modeling that, it's still social and that we're talking about a person today and a person tomorrow, and how do we aggregate utility across time? And so we can drop the intertemporal and just think about social welfare. So even in a one period solution, we've got the utility delivered to you, and we've got the utility delivered to me. And so then the question is, how do we balance your benefits and my benefits? There's going to be some things which, let's say we're voting or something like that, then there might be some people that get voted into office that more benefit me than you. Or there might be tax rates where a particular change in tax rates benefits me, but not you, or you and not me. And so the question for economists is, how do we deal with balancing these things? And one way to do that is to aggregate everyone into a single social welfare function, which somehow represents the aggregate welfare of a society at a given time across people. But then the question is, what is the right form of that? And really these next couple of slides is I'm just trying to motivate that maybe this isn't the right way to think about social welfare. This is the kind of standard way people start thinking about social welfare. But as we'll talk about starting next week, we should probably go back to our Pareto optimality to think about that, to think about a sort of a better way to think about social welfare. But if we think about social welfare within a period across people, like we think about social welfare across time periods for a single person, then we can imagine that, we're just looking for the right social welfare function, or SWF, social welfare function. And then we can start interpreting, what do these different functions mean? And so normally in class, we would have sort of a discussion about what these things mean. So I want you to stare at these things and think about, if these are my social welfare spaces where my value is on the y-axis, the vertical axis, and your value is on the x-axis, and these are the indifference curves that correspond to different choices of social welfare function, then what do each one of these mean? What does it mean to have horizontal indifference curves? What does it mean to have vertical indifference curves? What does this thing mean with the squares here? So think about that for a second. Just stare at these. And think about, before we move on here, think about which one of these, if you're focused on just your utility, which one of these is going to best benefit you? If you're focused just on my utility, which one of these is best going to benefit me. So if we look here, let's say this one, notice here that the indifference curves are horizontal, which means that regardless of how we allocate utility across you on the horizontal axis or me on the vertical axis, then what we see is we don't actually care at all about whatever the utility is in the horizontal direction. So if I am sitting here and I have this utility, so I'm feeling this good or whatever, if someone makes a policy change that doesn't change my utility at all, but it does cause you to move down in utility significantly, then it turns out that our social welfare function that aggregates these basically doesn't pay any attention to what it did to you. So this social welfare function that's horizontal right here basically means that the social welfare function is only, it depends only on me. It's only my utility. So it's as if I don't care at all about you, it's just me. Anything that increases my benefit increases society's benefit, and maximizing society's benefit is maximizing my benefit, regardless of what it does to you. That's what a horizontal social welfare function would look like. Flip that, and you get, this case here. And this case just turns that around. And this says that now all we care about is your value. So this is saying that as long that we only are interested in movements along your value. If we make any movements along my value that don't change your value, they don't get paid attention to. So if you were to maximize this social welfare function, then that would be equivalent to just maximizing your utility. It's just focused on you. Now, neither one of those are practical, but they allow us to think more critically about this function over here. And what this function over here does is, notice there's this strong diagonal. And if you remember that on the upper part of the diagonal, then basically this is where my utility, so I'll say this is my utility, is greater than your utility. And on the lower diagonal, your utility is greater than my utility. And across the diagonal, our utilities are equal. And so we know that the vertical case favors you. So I'm going to put you here. And we know that the horizontal case favors me. And so a funny looking utility function, or the funny looking utility function that has indifference curves like this, is a social welfare function that favors the individual that has the least welfare. And so maximizing this social welfare function means maximizing the minimum utility across society. So this, if you say that this here is the social welfare function that we are focused on, then what you're saying is we are going to ignore people who are doing really, really well, and we are going to focus all our efforts on people that are doing very poorly, and we are going to try to raise them up. And raising them up may pull some of those higher people down, but we don't care about anyone unless they're at the bottom of the utility ladder. That's what this social welfare function means. So sit and think about that for a second before we move on. If you have any questions about that, then this is a good time to post those in the questions there. Maybe I'll put that slide back up there. So that's the way I want you to think about these things as you're staring at these things, is try to think about what are the societal implications of assuming social welfare functions of particular shapes, because people do that, economists do that, is that they'll go out and they'll assume a certain shape of a social welfare function. You have to be able to look at the shapes and see the assumptions. When the shape is horizontal, then it's ignoring one group, vertical, ignoring another group. When it's kind of shaped like this over here on the right-hand side, then it's sometimes ignoring one group and sometimes ignoring another group based on context, based on who's kind of in the who's doing the worst at the time. And then there are other things we can think of. So like this is one way we perturb things, where here these lines are not quite horizontal, but they are pretty darn shallow. So what that tells me is that I do care about your welfare, your utility, but I mostly care about my utility. So this is telling me that I would exchange a lot of your utility for a small increase in my utility. So I'm willing to make you feel a lot worse to make me feel a little better. But I do care a little bit about you, and that's what this utility function is. And likewise, if you made them really steep, it'd be the other way around, where in that case, I would be willing to, or society would be willing to penalize me greatly just to increase your benefit just a little bit. So again, that's a way to interpret these things. And then over here, you can kind of think of this one as kind of a tempered version of the minimax criteria. So in the or the maxi-min criteria. So in the maxi-min criteria on the previous slide, then what we were saying is that maximizing society's welfare would be bringing up the individual that has the least amount. Well, this here is kind of saying that, well, in essence, that's kind of what we're doing, is we really care about the individual that has the minimum amount. But when that individual starts accumulating utility, and when the gap between the individual with the minimum and the individual with the maximum is narrow, then we're going to start balancing the two of them so that it acts a little bit more like one of these. So like out here, it acts, and out here, at that point, we are just trying to raise up the individual that's got the least. But in the middle, we are now balancing those individuals. As the individuals get closer and closer together, and society becomes more and more egalitarian, then we start kind of favoring everyone roughly equally. And so when these things reach like 45-degree lines in the middle here, then we do favor everyone equally. And then over here, in this example here, where everything is a 45-degree angle everywhere, then what we're saying over here is that we always favor everyone equally. This is like in the intertemporal case, this is like saying, I'm willing to take rewards later or now, I don't care. It's all the same to me. In this case, we're saying to maximize society's welfare, maximize anyone's welfare, and I'm happy about it. And because effectively what we're saying here is that the social welfare is just equally you plus me. Your benefit plus my benefit equally, no scalar on either one. So if you were to say, I've got $1, who should I give it to? So rather than saying, well, give it to the one that has the biggest bang for your buck, then you can say, give it to either one of them. I don't care. Give it to you, give it to me. It's going to increase society's welfare by $1 regardless. If I, over here, then I better give the $1 to me, because society's social welfare is benefited most by increasing my welfare. But over here, it doesn't matter who I give it to. That's what these shapes mean. So there's one more shape that I want you to be familiar with as we look at these social welfare functions. And again, we're going to abandon this social welfare approach as we move into next week and try to take on a more Pareto optimal approach. We're going to revisit that. But there is one more condition that we think about when we talk about social welfare, and that's the so-called equal respect condition. And this equal respect condition means that when you plot the indifference curves of a social welfare function, then they're symmetric around the diagonal. So if I draw a diagonal through here, I tried to draw a diagonal here, or a diagonal through here, I could fold the indifference curves along that diagonal and they would lie right on top of each other. And that is this so-called equal respect condition. And this equal respect condition, I'm asking here, like, you might think about, like, why might we call that an equal respect condition? And if you remember when we motivated this, you know, what was going on here, then we first talked about all vertical lines and then all horizontal lines and then combined them together. And all vertical lines sounded really harsh and all horizontal lines sounded really harsh. But when we combined them together, it sounded pretty good. It's like, yeah, okay, I get it. Society benefits from lifting up the individual who's doing the worst. That sounds great. And what equal respect condition means is that we are going to give everyone, we're not going to weight anyone more than the other. So in the left case here, that's sort of one extreme case of that, where everybody is equally valid and we don't care where anybody gets the benefit. And then over here, it's a little different than that, where we say, well, we do care where the benefit goes. The benefit should go to the individual who's doing the worst, but we don't have any intrinsic bias aside from that. So it's all kind of like, we prefer you when you're doing the worst, and we prefer me when I'm doing the worst. As long as we know who's doing the worst, that's who we prefer. So we have respect. We have so-called equal respect. So when we study social welfare curves, when they have this symmetric shape, then it has this so-called equal respect condition. Why is this important? Well, the people who do mathematics in social welfare sometimes assume things like, we're going to assume the equal respect condition. That allows them to assume, that allows them to not have to pick one social welfare function. They can say, our mathematical results will hold so long as the social welfare function is symmetric, so long that it can be folded along this diagonal axis, and then our mathematical results will hold. And that's why they have this so-called equal respect condition, because it's really hard to choose the right social welfare function. And that's why moving forward, we're going to try to abandon the social welfare approach and think in terms of Pareto optimality. And as you'll see moving into chapter 3, the Pareto optimality that we've already learned about is a little flawed. And so we're going to need to kind of fix Pareto optimality to make it practical before we can really move forward with it. And that's what we're going to talk about in chapter 3 and starting with the next lecture. So for now, are there any questions about the equal respect condition, etc.? Again, if there are, then I recommend posting to Slack, posting to the discussion boards, using the questions link that I put in the chat or that's on the screen right here, sending me an email, sending the TA an email. These are all excellent choices if you've got questions about this stuff. Okay. So just reminders moving forward, you should start reading chapter 4 and chapter 5. Chapter 4 is pretty short. I am going to do my best to have a Canvas activity that is available to you. Probably focusing more on chapter 5, so look out for that. And we go back to synchronous on Tuesday, so look out for that. And their homework due Sunday, and the muddiest point due Sunday. And then I still should have my office hours today at 4 p.m. Thursday at 4 p.m. as usual, and then again Monday at 4 p.m. All right, so with that, let's do, this is the last slide. One last attendance exercise. So I will put the attendance exercise in the chat, the link to the chat, so that you can find that in the chat, or you just use this. And the question that I have for you is, what is the social welfare function condition called when the social welfare function is symmetric along the diagonal axis? That's the question that I have. So what is the social welfare function criteria called when the social welfare function is symmetric along the diagonal axis? So I have about 24 hours to fill that out, to get that finished. Have any questions, let me know. Otherwise, we'll see you on Tuesday. Homework, Muddy's Point due Sunday. Have a good weekend.